Okay, so this is just a little demonstration of using Audacity to measure sounds from our voice. Hopefully this is helpful, and you might notice that we need to make sure that we have mono recording, and if there's more than one microphone you might have to just check which one it is. Maybe if you just plugged one in you'll see it show up. If I do mono recording, which I'd like for you to do, it'll make things simpler. You can hit record, and I'll record and just record a couple of sounds with my voice. Ooh, ooh, ooh. And I'm also going to make one more sound that goes ooh. Okay. So here we have some fairly complex things going on here. We had one tone, another tone, another tone. So here's my three tones. I can do them all side by side here. And toward the end, I did something special. This is me talking in the center, and this is something special we'll take a look at right toward the end here. The way that we can take a look at this, we right-click. We can right-click with the hourglass, and we should be able to zoom in. Also, just clicking on the numbers, depending on what version you have of Audacity, you can click on the numbers on the side, and you can either zoom in or zoom out. Try to zoom in as close to whatever the center line looks like of this thing. If you zoom in this direction, it zooms in the Y direction. Now, something I want to bring to your attention here is that if I keep zooming in, I actually see these little points. These are the digitization. This is actually how a computer is measuring changes in pressure and then is converting it into a voltage. And so you can see here that it's gotten it down to some pretty there's a bunch of points that make up all these waves. And so if we zoom out again, we can actually see something that looks like the wave that we created. So anyway, let's take a look at our first one. I'm going to zoom in there, and you can see that it's a complex periodic waveform. I'm going to go to the cursor tool up at the top here, and I'm going to select 10 waves. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Those are my 10 waves. Now if you look down at the bottom here, you'll notice that it says start and end of selection. And so I can notice that I have 1.294 is the beginning of my 10 waves, and 1.357 is the end of my 10 waves. So one thing that might be interesting for us to do is to figure out, well, all right, well, how long then is one sound wave? What is the period of one of these periodic waves? And so if I open up my calculator here, I can, let me just go ahead and clear. I don't know how to do that. It's okay. Anyway, I can take a look at this here. I'll say 1.357 minus 1.294. And just where am I getting those numbers? That's down here at the bottom, 1.357, 1.294. When I go there, it gives me 63 milliseconds. Now, I can also put this into just a regular decimal point here. So it's 0.063 here, which is the same thing as 63 milliseconds. So however you did it, so notice there's a little pesky decimal point down here at the bottom, so it's 1.357 and 1.294, right? So 63 milliseconds is a very short time, but that's actually for 10 cycles. So that number then, divided by 10, is actually this number here, and I'm going to actually increase my precision here. There we go. So I have 0.0063 as my time for one period. So that's going from here to here, for example. And notice that I didn't take like from one peak to the next little bump. I took from one bump to where it looks like it repeats itself. So I did actually like one high peak to the next high peak. And I found that it was 6.3 milliseconds, or 0.0063 seconds. If I do 1 divided by that, I'll do 1 over answer here, I'm going to get 158.7. And so if I put these together here, so I'm going to say that's 158.7 hertz is my sort of 1 over tau for this example here. I'm going to zoom out just a little bit here, and I'm going to compare this to the spectrogram. We do the spectrogram, we make spectrogram settings, and then we change the window size to 8192. This is going to give us better precision. And I'm going to zoom in here. Now you can see that there's certain places here where I have these lines. These lines are actually the different frequencies that I produce with my voice. Since it was not a simple sinusoidal waveform, there are actually several frequencies that are included in here. So you can actually see that the very first big one seems to be somewhere around 150. If I to make a selection with my cursor tool and do Analyze Plot Spectrum, I can actually see that there's a big peak right here at 153 or so. Well, maybe it's at 155, 158, something like this. But the point is that that big peak, that first big peak that we see, and by the way, you might have some noise in your example that goes all the way down to 0, but the first big peak that we see is 156, which is, I would say, close enough to the 158.7, which is what we recorded when we did 1 over the period. So you can also see that over here in the spectrogram. You have a 150, maybe it's a little bit more than 150, but it's certainly not as high as 200. And I can zoom in here if I want and see that it's centered around 155 or so, is this sort of this band. So this is an example of our spectrogram at 158. And let's just also go ahead and take a look at one of the other parts that we had measured here. So that was one frequency. I'm going to zoom back out again. Here was our next one. And if I look at this waveform, wow, this one looks also very complex here. If I look at this thing, you can see that actually there's sort of a periodicity. This, let's see here. I'll take the little one where it has the jump and then the next jump. So, in fact, maybe I'm going to pick this second one here, just so it's a little simpler. Maybe we'll. You can notice here that this is a very nice little sine wave that I made, basically. So here I can look for 10 oscillations, and I'll go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And you can see that I have 72 milliseconds minus 37 milliseconds. So again, I'm going to get out my calculator and I'll type in 72 milliseconds minus 37 milliseconds. That's 35 milliseconds for 10 oscillations. So that means that for one oscillation, I must have it in 3.5 milliseconds. If I take 1 over 3.5 milliseconds, that's 1.5 times 10 to the minus 3, I get 285.7 hertz. So that was actually a higher frequency than my first one. If I go back to the spectrogram again, I can zoom in to my first big line there. So you can see that big thick line there. I can zoom in, oops, and you can actually see that that line is centered around 280 or so, maybe 285. And again, I can also select some portion of this, analyze, plot spectrum. You see indeed the very first peak that I have here is around 276, okay, maybe 280. You can see that it's kind of a little bit of a range, right? There's some width to the peak. And that's normal. But nonetheless, that number is going to be corresponding to the 1 over the periodicity of my signal. So hopefully that helps get you oriented, reinforce your learning around how to use Audacity. We've now looked at those two different scenarios, but I wanted to actually look at one more, which is kind of the wild card that I had created there, which is when I made my voice go like, ooh, like that. So this is called as a chirp sometimes, and the reason is because birds make a sound where it goes from low frequency up to high frequency. So if I zoom in on this portion here, and then go back to spectrogram, you can actually see something very interesting here. The sound is at one frequency, and then it goes up to higher frequencies. And so actually you can actually really see that here in the data, that my voice is at lower frequency at around 130 hertz, and then as the next, let's say, okay, we can actually measure the amount of time here. It looks like over about 0.7 seconds that I went from a low frequency around 150 hertz up to a higher frequency around, say, 400 or 450 hertz. And you can see these other tones that are above here are actually the harmonics on my voice, and this is what makes each voice sound unique. And so you can actually see, if I plot the spectrum, see that there's a peak around, say, 125 or so. And then if I take another portion of the spectrum and plot that, you can see that it has now shifted up to 345. So I just wanted to give that other example as a way of understanding the different kinds of beautiful information that spectrogram can tell us. Whereas you could see this in the waveform. For example, let's zoom in here. You could analyze these waves here and look at, well, what's the period of these things here, and then go ahead and do the same thing down over here. But you might find that it's difficult to do that. It's not convenient, right? So this technology of spectrogram actually helps us to see that the spacing between the oscillations here is lower than the spacing between the oscillations over here. And so that is why we use a spectrogram to understand and to analyze the different types of sounds that we experience. Thank you for watching this video, and I hope this was helpful.